going going to learn process integration. Mm. The slide is available in Elite. I'm using two books to prepare this slide. Chemical process design. Process design. Chemical process design and integration. Chapter 16. And sustainability in the process industry by Jiri Clemens and others. Refer to chapter 4. Introduction. The need for the need for process integration. Energy and water saving, global warming and greenhouse gas emission have become major technological, societal and political issues. Therefore, numerous studies have been performed on the subject on improving energy efficiency while reducing emission of greenhouse gases, volatile organic compound and other pollutants. It has gradually become evident that resource input and effluent of industrial process are often connected to each other. Therefore, reducing wastewater effluent naturally leads to reduced freshwater intake. Process integration. Process integration. Process integration is a family of methodologies for combining several processes to reduce consumption of resources and or to reduce harmful emission. This energy-saving methodology have been used extensively in the processing and power generating industry over the last 30 years. Heat integration examine the potential for improving and optimizing the heat exchange between heat source and heat sink in order to reduce the amount of external heating and cooling required, thereby reducing cost and emission. The role of process integration in making industry sustainable. So sustainable development implies that current action should not harm future generation and that measurable indicators are needed to ensure compliance. For industrial process, the relevant indicators are the rate of resource intake and effluent emission. These factors are usually expressed in terms of footprints For example, the carbon footprint or the water footprint. And the sustainability of an industrial process depend on minimizing this footprint. For synthesis and design problem, the measured indicators should apply to the proposed system complete life cycle as part of a life cycle assessment. Example of applied process integration. Harela, Illas, and Ariola studied a hospital complex that included an institute, a general hospital, a regional laundry center, a sports center, and some other public building. This is heat energy integration for a hospital complex. The diesel fuel used to generate the steam required for complex amounted to 75% of its total energy consumption and 68% of its total energy costs. So 396,000 in 1999. The pinch analysis that was performed estimated the minimum need for external heating is at 388.64 kilowatt. Because the actual heating use was consuming 625 kilowatt, there existed a potential energy saving of 38%. Therefore, from pinch analysis, we can estimate the minimum heat for this process, example, hospital complex. Heat recovery problem identification. This is the step. First step is to inspect the general process flow sheet, which may contain heat recovery exchanger. Remove the recovery heat exchanger and replace them with equivalent virtual heaters and coolers. Lump all consecutive heaters and coolers. The resulting virtual heater and coolers represent the net heating and cooling demands of the flow sheet streams. The heating and cooling demands of the flow sheet stream are then listed in a tabular format where each heating demand is referred to as a cold stream and conversely each cooling demand as a hot stream. Example, a process flow sheet involving two reactors and a distillation column. The process already incorporates two recovery heat exchanger. The utility heating demand of the process is H equal to 1760 kilowatt and the cooling demand is 900 kilowatt. So this figure shows the flow sheet after step 1 until step 4. The heating and cooling demand of the stream have been consolidated by removing the existing exchanger. So you remove the heat exchange and the existing exchanger, reboiler and condenser duties have been left out of the analysis for simplicity. It is assumed that any process cooling duty is available to match up with any heating duty. So both heat exchanger is gone. Yeah. The most notable change is after the column. So outlet from the column is cool from 138 to 34 and the reactor is heated. The feed for the reactor is heated from 30 to 120 So each cooling and heating has its own duty. So applying step 5 to to the data in that figure produce the data set in table 4.1. By convention, heating duties are positive, cooling negative. The subscript S and T did not apply and target temperature for the process stream. The TS temperature supply is feed, temperature target is outlet. The CP can be calculated using the following equation. CP equal to this CP delta H over T target minus T supply equal to delta H over delta T. So for H1 example, the TS is 182 and cool to 78. So the tap is hot. So delta H is negative 2080 kilowatt, CP of 20. So H1 is here. So how about C3 condenser? So for C3, add reactor 1. Temperature TS is 30, T target is 120. So it's cold. See, for type hot, the TS is normally higher than TT. For cold, TS is lower than T target. So it's positive and CP is 36. This is referred to as data extraction. The problem table algorithm is another method to identify pinch point or pinch. Mm, Last week we learned about composite curve, limited composite curve LCC using graph. Now we use a numerical method to identify the pinch. The problem table algorithm, although composite curve can be used to set energy target, they are inconvenient since they are based on graphical construction. The algorithm will be explained using the data in table 16.24. Delta T mean equal to 10 degrees C. You may refer to chapter 16. Mm, Chapter 16, page 365. Okay, for the heat exchange stream data for the flowsheet 16.2. 16.2 we may refer to page 358. So for reactor 1, it's a call, so supply temperature is lower than target. Delta H equal to 32 CP of 0.2. So to calculate CP, use CP equal to delta H over T minus TS. Yeah. So step 1, determine the shifted temperature interval. This is we the step 1 for problem table algorithm. Determine the shifted temperature interval from actual supply and target temperature. Hot stream are shifted down in temperature by delta T min over 2, while cold stream are increased by delta T min over 2. So for Ts, this is cold stream. So for cold, you increase 20 to 5 degrees C because our T min is 10. So 10 over 2 is 5. 35, 185. For hot, you subtract by 5. So 250 to 245, 40 to 35, and so on. Second step is the stream population in figure 1616 with a vertical temperature case. So the temperature for y-axis here is T star, which is interval temperature. You already shift it. So shifted temperature have asterisk. The interval temperature shown in figure 1616 are set to delta T min over 2 below hot stream temperature and delta T min above all stream temperature. For example, so stream 1 here, it started at 25 until 135. The target is the actual target is 180, the actual supply is 20. So 20, 30, 70, 140, 180 is the actual temperature. 25, this is the shifted temperature. That one is for cold. So for cold is from upward trend, while for hot it's downward trend. So for example, stream 2 it's for 245 and down until 35. Yeah. And do it for other temperature, not for other, for other stream. Have 4 stream here. Step 3, heat balance is carried out within each shifted temperature interval according to equation below. So for this, delta H equal to CPC cold stream minus CPH hot stream delta T. So delta H here refer to delta H interval. It's similar to Cp equal to delta H over delta T. See. The result is given in figure 1617, in which some of the shifted intervals are seen to have a surplus of heat and some have a deficit. The heat balance within each shifted interval allow maximum heat recovery within each interval. However, recovery must also be allowed between intervals. So for calculation of Cp, for example, 35 until 75, how do you calculate 0.05 here? The arrow that pass through this interval Cp1 and Cp2, see here, this was sim1 and sim2. So the arrow upward is positive and vice versa, so downward is negative. So CPC means the CPH is 0.2, so for cold cold stream, same one here, is 0.2, one for the stream 2, it's cold hot stream. So minus 0.15 equal to 0.05. That's how you calculate. And so on for the other interval. Step 4. Cascade any surplus heat down the temperature scale from interval to interval. This is possible because any excess heat available from the hot stream in an interval is hot enough to supply a deficit in cold stream in the next interval. So you create a cascade. So here is the shifted temperature or interval temperature. This is the delta H. Yeah, delta H. Wait. That is delta H, yeah. Started from 0.25. Wait. Wait. First, assume no heat is applied to the first interval from hot utility figure 16.18a. The first interval has a surplus of 1.5 megawatt. Which is cascaded to the next interval. The second interval has a deficit of 6. Megawatt. So what does it mean is, wait, which if the heat calculated from this table to be negative 4.5 megawatt in the third table, the process has a surplus of 1 megawatt, which leave negative 3.5 to be cascaded to the next interval and so on. Some of the heat flow in the figure 16.18a are negative, which is invisible. So meaning, see here, it's you have a surplus and deficit. Therefore, to make the cascade visible, this cascade is not visible. Sufficient heat must be added from the hot utility to make the heat flow to be at least 0. The smallest amount of heat okay. To make the cascade feasible, sufficient heat must be added from hot utility to make the heat flow to be at least 0. The smallest amount of heat needed from hot utility is the largest negative heat flow from the figure 16.18a. So from 16.18a, the largest is negative 7.5 megawatt. In figure 16.18b, 7.5 megawatt is added from hot utility to the first interval. So from 7.5 here, we move it to hot utility here to here, then recalculate. Increases all of the heat flow between interval by 7.5 megawatt, giving one heat flow of just 0 at an interval temperature of 145 degrees C. More than 7.5 megawatt could be added from hot utility for the first level, but the objective is to find the minimum hot and cold utility, hence only the minimum is added. The point where the heat flow goes to 0 at T equal to 145 degrees C correspond to the pinch. So 7.5 minus plus 1.5 is 9, 9 minus 6, 3, 3 minus 10 plus 1 is 4, like that. And 4 minus 4 is 0. That's from figure 16.18b. This is 16.18b. QH mean equal to 7.5 megawatt. And QC mean is 10 megawatt. This correspond with the value, okay. If you prepare a composite curve, you will get the similar QH mean and QC mean. Thus, the actual hot and steam pinch value temperature are 150 and 140 respectively. So hot is 150 plus 5, cold is minus 5, 140. Because this temperature is interval temperature, shifted temperature. Another example, the flow sheet for a low temperature distillation process is shown in figure 16.19. Calculate the minimum hot and cold utility requirement and the calculation of the pinch. Assuming delta The flow sheet for a low temperature distillation process is shown in figure 16.19. Calculate the minimum hot and cold utility requirement and the location of the pinch, assuming delta T min equal to 5 degrees C. So the first thing to do is to extract the data. The stream data, so the extracted stream data is as follow. So we have fit to column 1. Fit to column 1, temperature supply is 20. the target temperature is 0. See, so 20 target is 0. So this is a heat exchanger. So this is a hot stream because Ts is higher than Tt. The delta H is negative 0.8 for hot is negative. Therefore, Cp is 0.04. So Cp is equal to delta H over Tt minus Ts. Similar for condenser 1, what is it? Column 2, column 2 condenser, column 1 reboiler, column 2 reboiler, column 2 bottom, column 2 overhead. Yeah. So 1, 2, 3, 4, 7. So we have 7 stream. For hot stream, the delta H is negative and vice versa. Hot stream can be identified if the hot stream can be identified if the supply temperature is higher than target temperature and vice versa for cold stream. Step 2, calculate the shifted interval temperature. So for shifted interval temperature, follow the rule of thumb. Hot stream will be shifted down by 2.5 degrees C. 2.5 because delta T min is 5. So shifted is delta T min over 2. So 5 over 2 is 2.5. For cold stream, it's increased by 2.5. As shown in table 16.5. So yeah. So for hot, so for stream 1, 20, the shifted TS, actual TS, which is just supply is 20, the shifted is 17.5. And the TT is negative 2.5. And follow the, but for coal, you increase it by 2.5. See, from 19 to 25.5, 20 to 22.5. Step 3, carry out the heat balance within each shifted temperature interval. So do the interval temperature. So interval temperature here is, you get it from TS and TT. So for example, stream 1, it's hot. So from 117.5 degrees C to negative 2.5 degrees C. Okay. Once you carry out the heat balance, determine the CP. Yeah. So CP, how to calculate CP? It's 0 because there is no arrow. For example, 37.5 until 41, negative 41.5. Yeah, you see here. There is no arrow crossing this interval, so there is no CP. But for cases like this one, yeah. So see here, the CP is 0.77. So 0.8 minus 0.0 4 plus, sorry, 0.81. So 0.8 plus 0.01 minus 0.04. So you get 0.77 ZPC. In similar for other. So delta H here interval is 1. Delta H is equal to CPC minus CPH here, value here, times interval delta T. So you get the delta H. Step 4, create the heat cascade with zero hot utility. So start with zero, meaning start with zero hot utility. This lead to negative heat flow, the largest of which is negative 1.84 megawatt. Next is adding 1.84 from hot. So once you determine the largest here, so bring this largest to the hot utility up there. So we calculate it. Adding 1.84 megawatt from hot utility give QH min is 184 megawatt. QC min is 184 megawatt. Hot stream pinch temperature is negative 19 degrees C. And cold stream pinch temperature is negative 24. This 21.5 degrees C is just a shifted temperature. So for hot stream, you need to add by 2.5. For cold stream is minus 2.5. Yeah. So yeah, that's all. So if you use composite curve, you will get a similar hot pinch temperature. After maximizing heat recovery in the heat exchange network, outdoors heating and cooling duties not serviced by heat recovery must be provided by external utilities. The most common hot utility is steam. The high temperature heating duties require furnace flue gas or hot oil circuit. Cold utilities might be refrigeration, cooling water, air cooling, and furnace air preheating. Now you will learn how to construct a grand composite curve. So this is a tool to understand the interface between the process and the utility steam system obtained by plotting the problem table cascade. The problem table cascade is this one with pinch, meaning the hot utility is not zero. Temperature plotted here is the shifted temperature. The hot stream are represented by delta T min over 2 colder. The cold stream is delta T min over 2 hotter. So this is the shifted temperature. The point of zero heat flow in the grand composite curve in figure 16.24 is the pinch, heat recovery pinch. The open jaw at the top and bottom are Q hash min. This is Q hash min. This is the QC min. The shaded areas known as pocket of heat recovery. In the pocket, a local surplus of heat in the process is used at temperature difference in excess of delta T min to satisfy a local deficit. This reflects the cascading of excess heat from high temperature interval to lower temperature interval in the problem table algorithm. Pinch, yeah. Example, the problem table cascade for the process in figure 16.2 is given in figure 1618. This is figure 16.2. So from here, you need to extract the data, then create the table cascade like this. So using this table cascade, problem table cascade, draw the grain composite curve. The grain composite curve is del T shifted versus delta H. So, okay. T shifted versus delta H. Yeah. Okay, delta H. So for two steam, so using green composite curve to determine these two conditions. For two level of steam at saturation condition and temperature of 250 degrees C and 180 degrees C, determine the lot on the two steam level that maximize the use of the lower pressure steam. So for delta T min equal to 10 degrees C, the two steam level are plotted on the grain composite curve at temperature of 235 and 175 degrees C. This is for two level of stream. This figure show the lot that maximize the use of the lower pressure steam. Calculate the lot on the lower pressure steam by interpolation of the cascade heat flow at T asterisk equal to 175. So for 175, you need to conduct a interpolation between 185 and 145. Why 185 is here? 145 is. So 175 is in between this interval. For here represent 4 megawatt for at 185 degree C minus 0, but 0 because at pinch 145 degree C theta H is equal to 0. So lot of 180 degree C steam is equal to 3 megawatt. For lot of 240 degree steam, it's straightforward. 75 minus 3, so 4.5 megawatt. Because for 240, the steam level is 235. The shifted temperature is 235, which is here. So it's in between 245 and 195. Just minus 75 and 3. Get the 4.5 megawatt. How about if we use hot oil for hot utility requirements? So second question is figure 16.26b. Sorry, Instead of using steam, a hot oil circuit is to be used with a supply temperature of 280 degrees C and Cp equal to 2.1 kilojoule per kilogram Kelvin. Calculate the minimum flow rate of hot oil. So for this case, if the minimum flow rate is required, then this corresponds to the steepest slope and minimum return temperature. So for minimum return temperature is the pinch temperature. Pinch temperature for this is 145, but the one is shifted. So for hot stream, U plus 5. For temperature, minimum return temperature is 150 degrees C. So make a line at 280. 280 because say here with a supply temperature of 280 for that hot oil. So 280, then from 150, find the steepest line that intersect 280. The steepest line. So the steepest line here intersect the grain composite curve. So at the intersection, find the delta H, which is 7.5 megawatt. So 7.5 is equal to 7.5 times 10 to the power of 3 times 1 over 22.1. 1 is Cp. So the delta T is 1 over 280 minus 150. The minimum flow rate is 27.5 kilogram per second. Thank you. Don't forget to do the activity in Ellipse for your attendance.